Welcome again, everyone. Today we will be discussing general curvilinear motion. So this is now the part 4 of our lecture series in dynamics of rigid bodies, wherein we will discuss the motion of a particle or an object in a three-dimensional curvilinear path. So let's start by describing the general curvilinear motion. It occurs when a particle moves along a curved path, and since this path is often described in three dimensions, the ideal solution will be using a vector analysis to formulate the particle's position, velocity, and acceleration. So we will define the particle's position, velocity, and acceleration in terms of vector analysis. So let's have here a figure of a particle with a reference point O, and the particle is located at a point on a space curve, and the space curve is defined, or the motion of the particle is defined by its path of motion as shown in the figure. Now, the position of the particle is represented by vector r. So we have to represent the vector as boldface R. So if you want to learn about vectors, I have also uploaded lectures about fundamentals of vectors, operations of vectors, and representation of vectors in the statics of rigid body lecture series. So if you want to have a review about vectors, so you may want to watch that video. So let's proceed. The magnitude of r changes as the particle moves along the path of motion. So if the particle moves to this position, so from the previous vector r, now we have another vector that is r1. So if again the particle moves, you can represent it with another vector that is r2. And suppose that during a small time interval, the particle moves a distance s along the curve to a new position. So we can have now the new position vector of the particle as it translates from its original position. So if originally the particle, or the initial condition of particle is here, then it moves to this point, there is a displacement represented by delta s, or it could be defined by vector delta r. Now from addition of vectors, we can say that this r prime, or vector r prime, is the sum of vector r, so the vector which represents the position of this object, plus vector delta r, which represents the change in position of this particular object. Now if you connect the tail of vector r and the tip of vector delta r, you will have the resultant, which is r prime. So now we can say that r prime is the sum of the initial position of the object represented by vector r plus the displacement, which is represented by delta r. So rewriting to get delta r, we have r prime minus r. And now delta r is the displacement of the particle. So we will use this to evaluate the velocity of a particle in curvilinear motion. So now the velocity of particle during the time interval as the particle displaces from this point to this point, the time elapsed now is represented by delta t. And delta t is a scalar quantity, that's why it is written in italicized non-boldface. So the average velocity as defined in the first lectures in dynamics is delta r over delta t. This is different from the instantaneous velocity. As we recall, the instantaneous velocity is the point velocity or the velocity analyzed at differential time interval. But in here, this is not a differential time interval. We have an observation that is defined by delta t instead of dt. And here we can see now that if we assume that delta t approaches 0, therefore delta r becomes smaller and smaller, and so we have a differential r or differential change in position if we have a very small time observation. So when delta t approaches 0, that would be dt. So now we have the instantaneous velocity because we are having a very small interval of time. So we determine the very small displacement over very small change of time. So that's dr over dt. And as the value of delta r becomes dr, it becomes tangent to the path of motion. So as you can see here, delta r may not be perfectly tangent with the curve because as you can see, this is like a secant because it touches the path of motion twice. But if you try to reduce this into a differential segment, therefore it could be assumed that delta r touches the curve at one point, then it becomes the tangent of the motion path. Okay, so if you try to see if delta r touches the path of motion twice, but if you try to resolve this or to reduce delta r to approximately 0, this will touch only the path of motion once, so this will be again tangent to the path of motion. So this is not the differential, or this is not the instantaneous velocity, and this one is the instantaneous velocity. So now the magnitude of v, which is called the speed. So recall from our first lectures in in dynamics, that the magnitude of velocity is speed. So the magnitude of a vector quantity is a scalar quantity, and it is obtained by realizing that the length of the straight line segment delta r approaches as the arc length delta s. So eventually, as you try to see this one, the blue arc here is delta s, and this delta r is the direct change in position. They may not be equal if you try to zoom this out. This blue line here and the arrow length here is not equal because we are not analyzing a differential element. But as soon as delta r or the delta t approaches 0, this will we can assume now that delta r approaches the value of the arc length. So if you have a smaller element of analysis here, eventually delta s would equate or will be equal to delta r. So as you can see here, the equation explains it all, that as delta t approaches 0, this segment becomes smaller, therefore delta r gradually becomes delta s. And this equation becomes the ds over dt, or the instantaneous velocity. Now, the instantaneous velocity can now be written as ds over dt. Previously, we have written that as dr over dt because this is a vector quantity, v. Now, if we have the speed, which is italicized letter v, we have now the speed equal to ds over dt. Recall that this is a scalar quantity, not a vector quantity. Now, speed can be obtained by differentiating the path function s with respect to time. So now this equation of path of motion could now be analyzed, and we can get the velocity equation from the position equation. Now we have proven that if you differentiate the equation of the path of motion, you get the velocity equation. And from the principle of differential calculus, if we get the derivative of this equation, we get the equation of the tangents. So we can say now that the speed or the velocity is tangent to the equation of motion. And if the particle has a velocity and a change in velocity, we can now analyze the acceleration. So initially we have the velocity at this point, which is tangent also at this point, and we have another velocity here represented by v prime. So there is an acceleration or deceleration for the object. So we can say now that v prime is equals to v plus delta v at t plus delta t. So if you have initial condition here, so the velocity of an object after some delta t, the velocity increases or decreases, and it changed to v prime. Now the change in velocity is represented by delta v. We can now say that v prime is equals to velocity plus the change in velocity at certain change of time. So the average acceleration, again not the instantaneous acceleration, could be defined by delta v over delta t. And we want to get the instantaneous acceleration. It has the same principle with analyzing or comparing average velocity to instantaneous velocity. So if your average acceleration is delta v over delta t, we will assume now, or we will let delta t approaches 0. So if we let delta t approaches 0, we will have a very, very small observation time of observation. Then the acceleration vector now is defined as the derivative of the velocity vector over differential time. And from here, we can see hodograph. So this is the hodograph. This is the graph of the hodograph shows the velocity. So as you can see, acceleration is directed here, and this is your hodograph. So now we can recall that the velocity vector is tangent to the hodograph, but since the derivative of velocity is the acceleration, therefore the acceleration vector is not tangent to the path of motion. And we can define now, since the acceleration vector is equal to the derivative of velocity vector, and recall that the velocity vector is equal to dr dt, we could replace this equation with this one, and they yield to this equation of acceleration. So by definition, the derivative A acts tangent to the hodograph, because this hodograph represents the velocity as a function of time, and the path of motion here. So recall that the velocity is tangent to the path of motion, but the acceleration is not tangent to the path of motion, but is always tangent to the hodograph. Because if this is defined by velocity as a function of time, if you get the derivative of this equation, that would be acceleration. Therefore, acceleration is tangent to the hodograph, but is not tangent to the path of motion. And velocity is tangent to the path of motion, but is not tangent definitely to the hodograph. Now let's represent the particle in a 3-dimension using rectangular components. So if you have a particle here, it can be described along a path that can be expressed in terms of x, y, and z components. So it is easier for us to define the position of this object if we use the global axis x, y, and z with base vectors I, j, and k. So to do that, we use vector r as position vector. Now we get the component of an object's position in terms of x, in terms of y, and in terms of z. So if a particle is at point x, y, z, for example, in this case, and the curved path is shown as S in here, the location of this particle is represented by a vector equal to this one. So as you can see, the I, which is the base vector for x component, is this one, or the value of x. The j is the base vector for y, and k is the base vector for z axis. Now you can say that an object or a particle in 3-dimensional curvilinear motion could be represented by this vector r. Now, the components of r will be functions of time and having a magnitude. So the magnitude of the position could be determined by using the Pythagorean theorem for 3-dimensional axis or for the rectangular coordinates, 3-dimensional rectangular coordinates. So to get this magnitude or the position of this particle relative to the origin of this one, you will use the Pythagorean theorem, which is the magnitude of this vector r is equal to the square root of the sum of the square of its component. And therefore, the first time derivative of r yields to the velocity of the particle, because we have discussed that the first derivative of the path of motion is the velocity equation. We have discussed that. The equation of path of motion, if you get the derivative, you will get the velocity equation. So to have that, we will simply get the derivative of the position equation. So if your position equation is r or vector r, we will get the derivative of this vector r to get the velocity vector. Now this velocity vector is equal to this one. So we have to expand this equation. So as you can see, the velocity vector is equal to this one. I just put it at the top. So represented in 3 axes. And let's try to get the derivative of each term. Now, if you try to use the multiplication derivative of 2 of x and I, so you will use this as u and v. Recall from your calculus. Now, the derivative of 2 terms u and v could be u times dv, or you may want to get v plus du first. So let's have v plus du, v times derivative of du plus u times derivative of v. Now, let's get v derivative of u. So you just have to copy v and get the derivative of u, that is dx over dt, plus you copy this one and then you get the derivative of this one. So that's just for this term. We will get the derivative of these three terms individually and then add them up. But as you can see, this term is 0 provided that XYZ reference frame is fixed, and therefore the direction and the magnitude of I does not change with time. Because this is a global axis, your DI does not change in time. So the direction of I remains the same, therefore DI over dt is 0. So differentiation of J and K components may be carried out similarly. So if you treat this one di over dt, this term would be 0. What remains on the expansion of this term is only this term, the dx over dt times I. Now if you perform the same thing on this, what remains would be the dy over dt times j, because the dj over dt would be 0. So what we have now would be this equation. So dr over dt would be vxi plus vyj plus vzk. So as you can see, this one is vx. So if you try to solve again for this one, you would what will remain will be vy, and for this one, what would remain would be this one. Okay, now we have the velocity vector equal to vxi plus vyj plus vzk, and we might want to rewrite vx, vy, and vz, so we can represent vx equal to x dot, y dot, and z dot respectively, and it represents the first time derivatives of x as a function of time, y as a function of time, and z as a function of time. So to get the velocity of an object, so the first thing we do is to get the derivative, the velocity along x, velocity along y, and velocity along z. But if we want to get the velocity of the object or the resultant velocity of the object, we still need to use the Pythagorean theorem. So as you can see, when we use the vector v, we can only tell the velocity along x, the velocity along y, velocity along z, but not the velocity of the object. So if you want to get the velocity or the speed, the magnitude of velocity or the speed, we need to perform the Pythagorean theorem. So that is the square root of the sum of the velocity, square of the velocity along x, square of the velocity along y, and square of velocity along z. So that would be your velocity. So to get the direction of the velocity, that is simply by having the unit vector of the velocity vector. So to get the unit vector of v, or the unit vector of the velocity vector v, you simply divide it with its magnitude. So you want to learn the unit vector, I have also uploaded it in my other lectures in statics. And also, if we know the velocity vector, we could get the acceleration vector in the same manner. So we have the velocity vector. So recall that if we get the derivative of the velocity vector, we will arrive with the acceleration vector. Therefore, your acceleration vector now would be this one. So you just replace your Vx with Ax, and Ax now is the first time derivative of Vx, Ay is the first time derivative of Vy, and Az is the first time derivative of Vz. Likewise, Vx is the first time derivative of x, Vy is the first time derivative of y, Vz is the first time derivative of z. Therefore, we can say that Ax is the second derivative of x, Ay is the second derivative of y, and Az is the second derivative of z. They are all relative to t, or time. So as you can see, we can now represent Ax in terms of Vx prime or Vx dot or x double dot. When we say double dot, that means the function of x is differentiated twice. So as you can see, Vx is only x dot, but this time since we are having the acceleration, we get the second derivative of x dot. So that's the same for ay and az. So ay is y double dot or vy dot, az is z double dot or vz double dot. And the magnitude of acceleration can be determined by, so if we have the x component of acceleration, y component of acceleration, and z component of acceleration, we can get the magnitude of the acceleration by performing the Pythagorean theorem. And its direction is defined also by its unit vector, because the purpose of the unit vector is to give direction to the vector, or it states the direction of the vector. So if you want to get the unit vector, again, you just simply divide the vector A with its magnitude determined from the Pythagorean theorem. Now let's have an optimization problem. So we have here, at any instant, the horizontal position of the weather balloon in the figure is defined by x is equals to 8t, where t is in seconds. If the equation of the path is y equals to x squared divided by 10, determine the magnitude and direction of the velocity and the acceleration when t equals to 2 seconds. Okay, let's try to answer this problem. So our objective is to determine the velocity of this weather balloon and also its acceleration, but at certain conditions. So that means when t is equals to 2, we have to get the velocity and acceleration. So the acceleration might be different at some point or at every different point of the path of motion, and also the velocity. So they're all variables. So what the question asks is the velocity and acceleration at certain time, or at t is equals to 2 seconds, because the velocity and the acceleration might be different if you analyze it when t is equals to 1, t equals 3, or some other value of time. The velocity and the acceleration is different. So let's start. First, we have to get the x component velocity, or the velocity component in the x direction. So recall that we have the position equation, x is equals to 80. So this x is a function of time. So the position of the balloon along x-axis is defined by time. So if you have a greater value of t, definitely you would get greater value of x. So that means the weather balloon, as time goes by, it moves farther and farther away from point A, because as you can see from the equation, as t increases, the value of x increases. So this is now the position equation along x as a function of time. Now, we could recall that the velocity along x, or Vx, is the first time derivative of x. So to get the velocity equation, we simply get the derivative of x. So performing that, we get Vx is equals to x dot equal to derivative of 80, again with respect to time. Now differentiating 8t, we get 8. So now we have Vx equal to 8, and that is your velocity along x direction. Now we can see that there is a constant velocity about x-axis. But again, this is not the velocity of the object, this is only the velocity about x-axis. There's also a velocity about y-axis. Now let's determine the velocity component in y direction. So the velocity in y direction could be determined by having the position equation about y. Now, y is equals to x squared over 10, and we can get vy by simply differentiating the position equation in y component. So we get vy now, y now is equals to x squared, but as you can see, x is equal to 80. Therefore, this is kind of a parametric equation because y is not directly a function of t, but x is a function of t, so we can represent y, or we can get y in terms of t. Now, substituting the value of x, we get 8t squared. Now, to get the velocity about y, so we simply get the derivative of y, but make sure that y is in terms of t because you are differentiating it with respect to time. So differentiating 8t squared, we get vy is equals to 12.8t. So now we have vx, or velocity about x, is 8 and velocity about y is 12.8. I'm writing them up or summing them up here. Okay, so we write them up. We have vx and vy. We don't have vc because we are analyzing two-dimensional axis only. So our objective is to get the velocity when time is 2. So when time is 2, the velocity about x-axis is still 8 because it is constantly 8, or it has a constant velocity along x-axis. But the velocity about y-axis is variable because of the value of t here. So substitute the value of t equals 2 seconds to get the velocity after 2 seconds about y-axis. So substituting 2 to this equation, you get velocity along x, which is 8, and velocity along y, which is 25.6 feet. Now, we have velocity along x, velocity along y, but not really the velocity of the object. Now, to get that, we use the Pythagorean theorem, wherein we get the square of the components and get the square root of the sum. So we have vx squared equals to 8 squared and vy squared equals to 25.6 squared. Now, calculating that, we get the velocity or the speed of the object equal to 26.82 feet per second. Now, this is your velocity, this is your speed, but it is asked the velocity. So therefore, we need a direction because this is just a scalar quantity. So to get that, let's have the direction. So the angle of the velocity could be defined by theta is equals to arctan of vy over vx, because as you can see, this is vy and this is vx. Now, v is somewhere here. That is, v is tangent to the equation, to the path of motion. This is tangent, but we want to get the direction of that. So let's measure the velocity from the positive x-axis. Now to get that, we use tangent function because this is your vy and this is your vx. Now this is your theta. That's why we use tangent function. So substituting that, we get vy is equals to 25.6 and vx is equals to 8, and performing arctan function, we get the angle measured from the positive x-axis, 75.65. Now your velocity would be 26.2 feet per second squared at 75.65 degrees measured from the positive x-axis. Now our next objective is to determine the acceleration of the object. So if we have the velocity equation, we can now get the acceleration equation. Let's start with the x component. If we have the velocity equation about x equal to 8, if we get the derivative of this equation, we will have the acceleration equation. So the first time derivative of velocity equation is the acceleration equation. Now let's differentiate the velocity equation. So we have velocity equation equals to 8, then differentiating 8 is 0. Therefore, the acceleration about x-axis is 0. And we could justify that without calculation since the velocity is constant, therefore there is no acceleration about x-axis. And it is proven by differential calculus because if you differentiate a constant, it would be 0. So we have two ways of proving that the acceleration is 0. First one is that if the velocity is constant, there is no acceleration. And if the velocity is constant, if you get the derivative, which is the acceleration, you get also 0. Now let's get the y component acceleration. So having your y component velocity, so you have to get the derivative of the y component velocity, you will get the y component acceleration. So differentiating Vy, that is 12.80, yields to this answer. So your Ay now is 12.8. So that means there is a constant acceleration in y-axis. But we are asked to get the acceleration at certain condition when t is equals to 2 seconds. So now let's rewrite the equations above. So we have acceleration x is equal to 0 and acceleration y is constant. Therefore, at any point on the curve, there is a constant acceleration. As you can see, there is no equation of acceleration here in terms of t. So let's write that here. Ax is 0, therefore there's no acceleration in x direction. And ay, therefore, the velocity in y direction is constantly increasing at 12.8 meters per second squared. Now to get the magnitude of acceleration, we simply use the Pythagorean theorem. So the Pythagorean theorem states that the sum of the square of its component is equal to the square of its magnitude. Now getting the square root of the sum of the components, we get the magnitude. So ax, so substituting the value of ax here, that's 0, and substituting the value of ay, that is 12.8, and performing the operation as shown, we get the magnitude of acceleration equal to 12.8 meter per second squared. Not only that is needed, because it is also asked the direction of the acceleration. So to get the direction of acceleration, we simply use the arctan function. So the angle measured from the positive x-axis is equal to arctan ay over ax, and substituting the values, we have 12.8 over 0, and theta a is now 90 degrees. So there you go. We have now the velocity and the direction of velocity, the acceleration, and the direction of acceleration. Let's proceed to the next problem. So a particle travels along a straight line path which is equal to y equals to 0.5x. If the x component of the particle's velocity is vx equals to 2t squared in terms of meters per second, where t is in seconds, determine the magnitude of the particle's velocity and acceleration when t is equals to 4 seconds. Now, the objective of this problem is to determine the magnitude of the particle's velocity and acceleration. So what do we have? It's the velocity equation about x and the position equation in y, but this is a function of x. So the first thing we do is to get the velocity equation related to the position equation by this equation. Okay, so recall that velocity x is also dx over dt. Now rewriting this equation yields to this one. So solving for dx, we have dx equals to vx times dt. And integrating this equation, we get the integral of dx equal to x, and the integral of vx dt would give us the position equation. So why do we first determine this one? Since we have the position equation about y, let's have the position equation about x. So let's have first all the position equation, and if we have the position equation, we can determine one by one the velocity equation about x, velocity equation about y. Then the next one, we get the acceleration equation about y and acceleration equation about x. So first, let's just have the position equations. So we can see that the velocity equation could help us determine the position equation because they are related. So through this equation, it says that if we integrate the velocity equation, we get the position equation. Okay, that's why this is our first step, because we have the position equation in y, but we don't have the position equation about x. And that's what we need. If we have position equation about y and position equation about x, we could get the rest. We could get the velocity about x, we could get the velocity about y, we could get the acceleration about y, we could get the acceleration about x, as long as we have the position equation. But the thing here, or the twist here, is that the given is the velocity equation about x. And we could relate vx with x by integrating this equation. So going back to this one, we have x is equal to the integral of vx dt. Now substituting the value of vx equals 2t squared, so this one. So integrating 2t squared, that yields to 2 over 3 t cubed. Now we have the position equation about x and given the position equation about y. Now, this is your position equation about x, and as you can see, the position equation about y is a function of x. Therefore, it's a parametric equation. We can represent y in terms of t by substituting the value of x. So if your position equation y is in terms of x, it is convenient to replace x with the value of t. Now substituting the value of x here yields to this equation. So substituting this one and simplifying this equation yields to the position equation in terms of t. Now both position equations are in terms of t. So we have now position equation about x and position equation about y. It would now be easy for us to determine the velocity about x, velocity about y, and succeedingly acceleration about x and acceleration about y. Now let's start first with the y component velocity equation of the particle. So differentiating the y, or the position equation about y, gives us the velocity about y. So vy now is simply the derivative of y. I'm sorry, this is y. So substituting the value of y in this equation yields this one, and performing differentiation, the derivative of t cubed is the derivative of t cubed over 3 is t squared. Now we have vy. But recall that vx is already given. Now we have position about x, position about y, and from position of x we get velocity x, or reversely, from vx we get x. And from y we get vy. Now we have the two. We have vx and we have vy. Now one of the questions, or the objective, could be determined by simply substituting the parameter when t is equals to 4 seconds. Now let's get the velocity when t is equals to 4 seconds. I'm sorry, this is 4 seconds. So Vx now is 2 times 4 squared. So we have the velocity along x component equal to 32 meter per second. And Vy now substituting t is equals to 4 second. Velocity about y now is 16 meter per second. But as we have discussed, this is not the velocity of the particle. This is just the component of the velocity of the particle in x and y axis respectively. So getting now the velocity of the object, we use the Pythagorean theorem. So that is getting the square of Vx and adding the square of Vy, then getting the square root of the sum, we get the value of velocity of the object at t is equals to 4 seconds. We have now the velocity equal to 35.78 meters per second. So we have the velocity. Now our next objective is to get the acceleration. Since we have velocity about x and velocity about y, it is convenient for us now to get acceleration about x and acceleration about y. So this is simply by getting the derivative of Vx. So Ax is the derivative of Vx and Ay is the derivative of Vy. Now, the derivative of 2t squared is Ax, and therefore Ax is 4t. And proceeding with the y component, let's substitute t squared to this one. And then getting the first time derivative of Vy, that is 2t. Now we have two equations of acceleration for Ax and for Ay. Now rewriting that above or here yields the Ax and Ay. Now we get the acceleration of particle when t is equals to 4 seconds by simply substituting 4 to t. Now we have Ax is equals to 4 times 4. Therefore, the acceleration about x-axis is 16 meters per second squared. And we have Ay is equals to 2t. And substituting 4 to t, we have 2 times 4. Now the acceleration is equals to 8 meters per second squared. And these are the components of acceleration. To get the acceleration, using Pythagorean theorem and substituting the values of Ax and Ay and performing the operation as above, we have A is equals to 17.89 meters per second squared. And that's the answer to this second problem. Now let's have the third problem. The box slides down the slope described by the equation y is equals to 0.05 x squared in terms of meter, where x is in meters. If the box has x components of velocity and acceleration of Vx is equals to negative 3 meters per second and Ax is equals to negative 1.5 meters per second squared at x is equals to 5, determine the y components of the velocity and the acceleration of the box at this instant. So our objective is when x is equal to 5 meter, we have to get the y component of velocity and the acceleration. So what are the given? We have the position equation, y is equals to 0.05 x squared. Velocity equation about x, that is negative 3 meters per second. And acceleration about x, that is 1.5 meters per second squared. Now, let's have this equation. Vy is equals to the derivative of y. So this is the usual. So the velocity about y is simply the derivative of the position equation about y. So the velocity is a derivative of the position about y. So if we have the value of y is equals to 0.05 x squared, we can get Vy now. So your Vy is 0.10 x times x dot. So as you can see, if you get the derivative of 0.05 x squared, you get 0.10 x. But remember that as you get the derivative, you have dx over dt, which is also the velocity about x. So this is dx over dt. We have discussed that. Or that is also Vx. Okay? Now, since Vx is already given at negative 3 meters per second, we can now substitute the value of Vx in the equation. And when x is equals to 5 meter, so the value of Vx is negative 3. So this one, the value of x is 5, and the coefficient 0.10, we can now get the y component of velocity that is negative 1.5 meters per second. Now that's the answer. The second question would be the acceleration about y component. Okay, now we have the velocity about y component, we can get the acceleration about y. So by simply getting the derivative of that equation yields us to ay. So the derivative or the first time derivative of this equation is the acceleration about y. So performing the operation of derivative by using chain rule, so we have 0.10 x, then that will be x double dot plus x dot times 0.10 x dot, and substituting the values, we have 0.10, the value of x is 5, the value of x double dot is 1.5 because that is given. Acceleration, ax is also x double dot, we have discussed that, and x dot is negative 3, that's given. 0.10 times x dot is again negative 3. Now the acceleration about y is 0.15 meters per second squared, and that is your answer. We already have the y component velocity and the y component acceleration. Now for the last problem, for a short time the path of the plane is described by an equation y in terms of x, that is y is equals to 0.001 x squared, where y is in meters. If the plane is rising with a constant upward velocity of 10 meters per second, determine the magnitudes of the velocity and acceleration of plane when it reaches an altitude of y equals to 100 meters. Now, using the chain rule, we have the equation y in terms of x. Now, if we get the derivative of y, we get the velocity about y. So this equation is y, is your y. Now, getting the derivative of this one using chain rule, that yields to 0.002x. So the derivative of this one is 0.002x, but don't forget the x dot because this is your dx over dt. So now we get Vy. So in the event that y is equals to 100 meter, we have to solve for the value of x because that's the parameter. Y is equals to 100 meter. Now if y is equals to 100 meter, let's solve for the value of x because that is needed here. Okay, so if y is 100, what would be the value of x? So we get the value of x equals to 316.23 meters. So if when y is 100 meter, the value of x is 316.23 meter. Now substituting the value here, x. But we don't know the value of this one, but we can recall that the plane is rising with a constant upward velocity equals to Vy. So we have now Vy is constantly at 10 meters per second. So that is Vy. Now our objective is to get Vx, and Vx is x dot. So substituting the value of x and Vy in the given equation above, and recall that from the given, Vy has a constant value of 10 meters per second. Now, substituting the values, Vy is 10, 0.002, x is 316.23 when y is 100 meter, and we are solving for the x component velocity, which is x dot. The x component velocity now is 15.81 meters per second. So we can now determine the velocity. So we have Vy constantly at 10 meters per second, and Vx we have computed, which is the x dot. So we can get the velocity now by Pythagorean theorem, substituting the values of Vx and Vy from this equation. There you go. And then solving for that, we get the velocity equals to 18.71 meters per second. So we are only asked about the magnitude. So this is the speed of the plane. Now, from the velocity equation, Vx and Vy, we can get the acceleration equation. Okay? Recall that if we get the first time derivative of Vy, that is 0.002x, we get the acceleration about y. So this is your Vy, recall. Now getting the derivative of that using chain rule, we get 0.002x times the derivative of this one. So u times derivative of v. So we have 0.002x, and the first time derivative of x dot will be x double dot plus v x dot, and the derivative of u, which is 0.002, and don't forget the x dot because the derivative of this one is 0.002, and you have to add x dot. And substituting the value, since Vy is constant, the value of Ay would be 0. So if there is a constant velocity about y, there will be 0 value of acceleration about y. And substituting the rest of the values, we have 0.002, the value of x is 316.23, x double dot is the unknown, x dot is 15.81, 0.002, and 15.81 is the x dot. We can now get the x component acceleration equals to negative 0.79 meters per second squared. Now we have ax and ay, so ax is negative 0.79 meters per second squared, and ay is 0. Now to get the magnitude of the acceleration, we simply use the Pythagorean theorem, now substituting the values of ax and ay here, and performing the operation, we get the value of acceleration equal to 0.79 meters per second squared. And there you go. We have finished the problem, and I encourage you to answer the practice problems for more of the appreciation of this topic. So here is the practice problem. You may want to pause the video if you want to copy this one. These are the computations, and these are the figures. So thank you for watching the video. I hope you learned a lot today, and please watch the next lecture series in dynamics of rigid bodies. Now, if you have any question, you might want to comment below. Thank you very much.